Hi everybody, this is Dr. A with your third video on immunochemistry techniques. We're going to look at labeled immunoassays. Alright, so a quick review over the labels. So the labels can be of different types. They are affixed to the antibody or detector antibody or whatever signal we're trying to pick up to emit the signal. They're done by the manufacturers. So the enzyme labels are the most common. Although it's really actually gone more fluorometry and chemiluminescence. The most common enzyme labels, though, are horseradish peroxidase, alkaline phosphatase, and glucose 7-phosphate dehydrogenase. The enzyme activity may be monitored by the amount of product that is generated from the substrate or the effect of the product on a couple reactions. It could be also looking for substrate disappearance. And usually this is done by monitoring a color reaction and measuring absorbance or change in absorbance. So this is a pretty typical like ELISA plate where there is an enzymatic color reaction that takes place. The darker the color, the more concentrated than the sample was. There are also fluorescent labels. There are fluorochromes or fluorophores. There are compounds that will absorb radiant energy of one wavelength and emit a radiant energy of a longer wavelength in less than 10 to the negative 4 seconds, so really quickly. The emitted light is going to be detected at an angle of 90 degrees from the path of the excitation light by a fluorometer or a modified spectrophotometer. The difference between the excitation and emission wavelengths is usually 20 to 80 nanometers. So they're your glow-in-the-dark stuff. So we can tag antibodies with fluorochromes or fluorophores and then shine them with light and then detect light emitted, and we can see if they're there or not. Then the luminescent labels, so they emit a photon of light as a result of an electrical, biochemical, or chemical reaction. Luminol and acrydium esters are the most commonly used. Luminol was the first chemiluminescent label used in immunoassays, and it's a cyclic diacylhydrazide that emits the light energy. Think of your glow-in-the-dark glow sticks where you have to mix the compounds to get the chemical reaction that emits light. And then you also have the acrydium esters. They're a triple ring organic molecule. It's linked by an ester bond to an organic chain, and it can emit light. Then in the assay designs, we have competitive immunoassays. So in competitive immunoassays, a labeled antigen competes with the unlabeled antigen, which is in the sample, for binding sites on an antibody. The labeled antigen is constant and limited. As the antigen in the sample increases, as its concentration increases, more of the unlabeled antigen from the sample then will bind to the antibody, and so that would result in less binding of the labeled antigen. The relationship then between the antigen concentration and the signal coming from the labeled antigen is going to be inversely proportional. So the more of the antigen was present in the initial sample, the weaker the signal is going to be. You can have one-step or two-step competitive immunoassays. In the one-step, you're going to put the labeled antigen, the sample, and the reagent antibody all simultaneously incubated together, all in one step, and then you read. In a two-step, the sample and the reagent antibody are incubated first, then the labeled antigen is added, and then you have a measurement. In non-competitive immunoassays, the labeled reagent antibody is used to detect the antigen. Excess labeled antibody is required to ensure that the labeled antibody reagent does not limit the reaction. The concentration of the antigen is directly proportional to the amount of bound labeled antibody, and the relationship is going to be linear up to a limit, and then it's subject to the high dose hook effect. All right, so let's go through all the different labeled immunoassays. This is going to take a minute. We have first PETINIA, particle enhanced turbidimetric inhibition immunoassay. It is a competitive homogeneous immunoassay. The antibody fragments and the drug latex particles will bind to form aggregates that can increase the turbidity of the solution. The free drug from the sample competes for the antibody fragments, thereby decreasing the rate of particle aggregation and turbidity. The rate of aggregation is then inversely proportional to the concentration of the drug in the sample. The enzyme-linked immunosorbent assay, or ELISA, it's a non-competitive heterogeneous immunoassay. The ELISA is on the solid phase is going to be microtiter plates with either antigen or antibody adsorbed onto the plate. This is done by the manufacturer. The sample is added then to form an antigen-antibody complex. The plate is washed to remove any unbound material. So this is where it's heterogeneous. We have the separation, the binding on the solid phase and then the wash. And then enzyme labels are added and then washed again. And then the substrate is added, and that induces color change, and then the absorbance colored and all that is red. So these are representation of both. So in PETINIA, you have the antibody here incubated with the latex particles with the antigen bound to it. So these are reagents. And then you have a sample antigen that you're trying to detect, a drug of some sort. And so if there's just a little bit of the drug, some of it will link up on the antibodies, but a lot of the latex particle coated with the drug are going to be able to pick up and bind the antibodies and make lattices that are going to cause the sample to be really turbid. So low concentration means really turbid sample. And then if there is a lot of the drug in the sample, the drug will be able to bind all the antibodies, and therefore the little latex particles will not precipitate because there's not going to be enough antibodies to bind them to form lattices that are causing turbidity, so it's going to be not turbid or less turbid. And then there are different designs to the ELISA. In a direct ELISA, the antigen is adsorbed onto the plate, and then the primary antibody conjugate that's labeled can attach to it and with a substrate change. So the indirect ELISA is you're actually going to try to detect an antibody. So direct ELISA, you're detecting an antigen. Indirect ELISA, there's a capture antigen that's put on the plate. The antibody from the patient's serum is then going to bind on it if it's present, and then the reagent is going to be added that has antibody to the antibody, and labeled with an enzyme, and then you add the substrate. And if this is present, then if this antibody was present, then this reaction here will take place, and there will be substrate change, color change. Okay, the sandwich ELISA, very commonly used. So this one, in a manufacturer, they would coat the well with capture antibodies. We're trying to detect a specific antigen, and that will be captured on there, and then there's an antibody and antibody. So it's like the rest of the indirect ELISA reaction that happens. And then in competitive ELISA, then you have inhibitor antigen that is competing with sample antigen for antibodies that are labeled. So there you go. Those are different ELISA type designs. Then we have the EMIT, the enzyme multiplied immunoassay technique. It is used for drugs of abuse and therapeutic drug monitoring. It is a competitive homogeneous immunoassay. The drug or metabolite in the sample competes with a drug or metabolite that's labeled with an enzyme, and it competes to bind a reagent antibody. The more drug there is in the sample, the more it binds antibodies, and the more free enzyme there will be. And the increased enzyme activity causes a change in color. The concentration of the drug is directly proportional to free enzyme activity. So the more drug there is, the more it's going to compete and pick up, right, all of these antibodies. And so there will be very few antibodies left to bind on the drug that's labeled with an enzyme that's in the reagents, and that those, like if the antibody binds on it, then it prevents the enzyme from acting. So if there's a lot of drug in the sample, it will soak up all of these antibodies and leave the labeled antigens from the reagent free to react and cause a big color change. Okay, so a lot of drug in the sample, a lot of color change happens. If there's no drug in the sample, then all of the antibodies are going to stick on these labeled antigens with enzyme to label drugs with the enzymes, and it will block the color from happening, and there will be no color reaction. So here you can see the little antibodies. Where's my little cursor? Okay, right here. The little antibodies are covering up the enzyme. They're blocking the enzyme on that labeled, on that drug that's labeled with the enzyme, and that reaction can't take place. Then you have CEDIA, cloned enzyme donor immunoassay. It is a competitive homogeneous immunoassay. Two component fragments of an enzyme, which are each individually active, are in the reagents. These fragments can spontaneously reassemble to form the active enzyme. So we have part A, part B have to come together to make the active enzyme. One of the enzyme fragments is attached to the analyte of interest, so it's the labeled analyte, and the analyte enzyme fragment conjugate is still able to reassemble with the other enzyme fragment to form the active enzyme. So it's not in the way for the reaction to happen. If it is unable to do this, it will be because the analyte is bound to an antibody. So if the antibody binds, it will block it, but otherwise the labeled part A, if you will, can react with part B to form an active enzyme complex. So the sample plus the enzyme fragment analyte conjugate in the reagent plus the other enzyme fragment plus the antibody directed against the analyte plus the substrate from the enzyme are all incubated together, homogeneous. Throw it all in one big pot. Right, and then there's competition for the antibody occurs between the analyte in the sample and the enzyme fragment analyte conjugate. So high concentrations of analytes in the sample will bind a lot of the reagent antibodies. So then only a small amount of the enzyme fragment analyte conjugate will be prevented from forming the active enzyme, and then therefore doing the color change, due to the enzyme activity. And if there are low concentrations of the analyte in the sample, that means that a lot of the reagent antibodies will bind on the enzyme fragment analyte conjugate. That will prevent it from forming active enzymes and from doing color change. And so this one is directly proportional. So the higher concentration in the sample, the higher the color reaction is going to be. So here it is. We have enzyme part A, enzyme part B. They have to assemble together to be active, and then they have to act on their substrate to, once active, they can act on the substrate to cause a color change. So we label one part of the enzyme here, and we label it with a label that's equivalent to the analyte that's trying to be detected. Okay, so so these are done together by the manufacturer. We incubate with the other part of the enzyme and with the substrate with antibodies to the analyte being detected. And so in this on yellow is the sample. So if there's the analyte in the sample or not, all of these are incubated together. If analyte is present in the sample, it soaks up the antibodies, and therefore the enzymes can assemble and do work on substrate and do the color change. If there's no analyte in the sample, the antibodies will bind here on the analyte that's tagged on part A of the enzyme, and that will block it from assembling and forming the active enzyme, and there will be no color change or reaction. All right, so next we have the microparticle capture enzyme immunoassay, or MEIA. It is a non-competitive sandwich heterogeneous immunoassay. It uses the surface of microparticles to isolate the antigen-antibody complexes. So it's a technique in which the solid phase support consists of very small latex microparticles in a liquid suspension with specific reagent antibodies that are covalently bonded to the microparticles. The antigen, if present, is then sandwiched between the microparticle-bound antibodies and the antigen-specific enzyme-labeled antibodies. The glass matrix will trap these particles in the separation phase, and then the antigen-antibody complexes are detected and quantitated by analysis of fluorescence from the enzyme-substrate interaction. So you can see it here. So the blue here represents the glass matrix. The orange represents the microparticle that have been coated with a capture antibody. The blue here is the analyte of interest, and if it is there, it will be captured. The yellow is an anti-analyte antibody that has a fluorescent molecule attached to it. So you can see it's a sandwich antibody tagged with fluorescent, and it's the separation phase is the beads, the microparticles are going to be trapped in the glass matrix. And the chemiluminescent microparticle immunoassay, or CMIA, is very similar to this microparticle capture enzyme immunoassay, but it's a non-competitive, so it's a non-competitive sandwich heterogeneous immunoassay, but it uses a magnet in its separation phase to hold the beads that have covalently bound antibodies, and then the other difference is it uses a chemiluminescent compound label to detect the antibody. And the trigger reagent will produce light, and a photomultiplier tube is used for the detection. It is one of the most sensitive assays. So you can see here these little magnetic beads that are coated with a capture antibody. They capture the antigen, and then you have the detector antibody here with its little chemiluminescent compound. It looks like a little bit like it's glowing, but you would have also in that the trigger reaction. So there would be some wash steps in there where the magnet's going to hold these beads. And if there was no analyte, then in the wash step, everything would be washed off. You just would have the beads in this analyte, and when you add these and then wash, there was nothing that would bind. So anyway, it makes a sandwich here, and then once that sandwich is formed, you can add the trigger reagent, and then the chemical light will happen and can be detected. We also have solid phase fluorescence immunoassay, or SPFIA. It is like ELISA, but the label is fluorescent. And then you have particle concentration fluorescence immunoassay, or PCFIA. It is a competitive heterogeneous immunoassay. It uses polystyrene particles bound with antibody. They're used to localize a reaction and concentrate the fluorescence so it can be detected. There's competition between a labeled antigen and a sample antigen for the antibody that is bound to the polystyrene beads. And it can also be antigen-bound particles competing for labeled antibodies and sample antibodies. So you can use it to detect antigen or antibodies. And then you have fluorescence excitation transfer immunoassays. They are competitive homogeneous immunoassays that use two fluorophores. When the two fluorophores are close to each other, one will absorb or quench the light from the other. So this is represented here. So if they're close together, one overtakes the other where you can only see the one signal. The reagent antigen and the antibody are each labeled with a different fluorophore. And then the reagent antigen and the sample antigen will compete for the labeled antibody. The more unlabeled antigen binds to the labeled antibody, or if you will, the more sample antigen binds to the labeled antibody, the more the labeled antigen can be detected, because it's not going to be in close proximity with the labeled antibody, which could quench its light. Okay, so if you have, the antigen you're trying to detect is in the sample, it will pick up the antibody and have its signal, and then the fluorophore label competitive antigen will be able to glow, and so that would be directly proportional here. The more of sample there is of antigen in the sample, the more this signal is detected. But if there is no sample antigen present, then the antibodies will pick up all the fluorophore labeled antigens, but then will quench their light and overtake, and so you would only get the signal from the labeled antibodies. Then you have substrate level fluorescence immunoassay, SLFIA. It is a competitive homogeneous immunoassay. This one uses haptens. So haptens are small antigens that have to be bound to something in order for the reaction to happen. So a hapten is labeled with a substrate that produces a fluorescent product when catalyzed by its enzyme. So you have here represented a little hapten, the substrate, its enzyme. The enzyme catalyzes, make a product, and then the product emits the signal, which here is going to be a fluorescence. The substrate label hapten will compete with the sample hapten for the antibody. If it is bound by the antibody, the substrate label hapten cannot generate a fluorescent signal. So if there is a lot of the hapten or drug in the sample, you incubate it again with the label hapten, the enzyme, and the antibodies. The sample hapten will bind up all the antibodies, and then the labeled haptens will be free to allow the enzyme to do the reaction and for fluorescence to happen. And if there is not a lot of sample, then a lot of the antibodies then will bind on the labeled hapten and will block the enzymatic reaction, and you will not have fluorescence. Then we have fluorescence polarization immunoassay. It is a competitive homogeneous immunoassay. It uses polarized light to excite the fluorescent label. The polarized light passes through a filter, which makes the light waves parallel, only oriented in one plane. The emitted light from the fluorescent label can be polarized or depolarized. If it's polarized, it will just emit in the same plane as the excitation light. So then you have the hapten antibody fluorescein molecule. They're large, and therefore they rotate slowly so they can emit light in the same plane as the absorbed light energy, and it can be detected. But the small hapten fluorescein molecules are really small, so they rotate really rapidly and they interrupt the polarized light, and they basically emit no signal. So the polarized light emitted is always measured at a 90-degree angle from the excitation light. It's pretty typical of fluorescence. And the hapten molecules in the sample will compete with labeled hapten molecules for the antibody. So if there are no haptens or drug in the sample, then all the labeled haptens will bind the antibodies and make a large, slowly rotating molecule, which will emit the polarized light, which then you'll have a strong signal. So this is an inverse proportional step. So no drug in the sample, no hapten means strong signal. If the haptens are present in the sample, then it binds the antibodies, and then the small label haptens will rotate rapidly and emit less light, so you have a weaker signal. So this try to represent the labeled hapten here, captured bound with the antibody, causes it to rotate slowly, and therefore the fluorophore, when it gets the polarized light, can emit polarized light. And then in this one, I'm trying to represent here that little hapten with the fluorophore. It's just spinning so fast, it's just emitting in all kinds of direction. It just interferes with the light, and you will not get a signal. And so that's because the antibodies were picked up by the sample. The sample hapten picked up all the antibodies, and so you just have the labeled antibodies, the labeled hapten spinning like crazy and not being detected. Then you have DELFIA, dissociation enhanced lanthanide fluoroimmunoassay. It measures time-delayed fluorescence from the label europium, which is a lanthanide chelate. The assay design can be competitive, heterogeneous, or non-competitive sandwich immunoassay, and is very sensitive. And so this represents a non-competitive sandwich one, where you have the analyte of interest here in yellow, you have capture antibodies, and then you have antibodies labeled with europium. And then they will add the DELFIA enhancement solution, which causes the europium to release its little compound here that is lanthanide, I guess, that is going to work with the enhancement solution to create the signal. And so there's a little bit of delay between this happening and the signal happening. So that's why it's a little bit delayed. It's a time-delayed fluorescence. It's very sensitive. It's a really good one. And then we are going to go into our immunoblots. So we have the Western blot. It's a transfer technique that's used to detect specific antibodies. So multiple protein antigens are acylated, denatured, and then separated by electrophoresis, specifically the sodium dodecyl sulfate polyacrylamide gel electrophoresis, also known as SDS page. The SDS component will denature the protein and adds an overall negative charge to the protein that's proportional to the molecular weight of the protein. The page electrophoresis allows for separation of the proteins based on their molecular weight. And then, so once you've done the SDS page and they've separated into the gel, then there's the blotting. So you transfer the proteins from the gel and you blot them onto nitrocellulose sheet. So that's the blot. And then you take the nitrocellulose sheet and you incubate it with labeled antibody. So this is the immunoblot, or the staining of the blot here. And then those radio-labeled antibodies can be autoradiographed, and you can develop it and fix it, and you can see the antigen bands. They are visualized. There is also immunocytochemistry and immunohistochemistry. Those are methods used to detect antigens in cells or tissues. With direct testing, the antigen is an integral part of cell or tissue, so you're directly staining the cell or the tissue. With indirect testing, the cells or tissues are used as a substrate to capture a serum antibody. The fluorescent labels are most commonly used with these methods, and they are portrayed right here. And then lastly, we have immunophenotyping. It is a technique that uses a flow cytometer to detect intracellular and cell surface antigens. It is used to classify cell lineages and identify stages of cell maturation. So this can aid in the diagnosis of leukemias and lymphomas. It begins with a living cell suspension, and then an aliquot of cell suspension is incubated with one or more monoclonal antibodies. If the cell expresses the antigen, then the labeled monoclonal antibody will bind and the fluorescent labels can be detected. This is an example here looking for the CD19 marker. If it is present, all the cells that glow, its presence, and then there's other ways where the signals can be detected here, and graphed, etc., etc. So anyway, that wraps up all the label immunoassay. I know this video was a lot longer. I hope you did benefit from it though. And I do thank you for your kind attention.